someone read the problem, please?
4x plus 1. No, wait, no, plus 1. 2x.
2x minus 3y. So this is just FOILing.
Yeah.
So this guy times this guy. We have 8x squared. Are you okay with that? And then, so first outside, so we do the outside, guys. And we have 4x times negative 3y, which is negative 12xy. And then we do the inside. We have y times 2x, which is positive 2xy. And then the last guy we have negative 3y times y, which is negative 3y squared. And so the only like terms that we have here are these two. Their variable components match exactly, so let's keep that in mind. Okay, can you put your phone away, please? I shouldn't have to ask you guys. There's no phones or anything like that, your phones. So these two are alike. So we have these match. So I'm going to go ahead and combine them. And I would have 8x squared minus 10xy minus 3y squared. Now we do a simplified, expanded form of this expression that was given. So again, the variable components must match exactly in order for you to combine them. But that's not the case with multiplication. Only for addition or subtraction. So these last couple warm-up problems here. Number 4, we're just distributing the 3a. You should have gotten 12a squared plus 3a. Number 5, you should have gotten 20x squared minus 3x minus 2. And number 6, we should have gotten 15y squared plus 22y plus 8. Number 4, you should have gotten 12a squared plus 3a. There's all 6. I feel like a good refresher on FOILing. We'll need more time.
Wait, how do you get 16x from the first?
Negative 16x?
Yeah.
If you FOIL everything, you're going to have two like terms. One of them is negative 12x, and the other one is negative 4x. And negative 12x plus negative 4x is negative 16x. If you're getting the wrong expression, one thing you might do is change all of subtraction to addition. It can usually avoid making a silly mistake. And just make sure also when you add negative numbers, how to add them properly. Be very careful. Okay. Let's move on. So just some basic translations, basic transformations. So a translation is a type of transformation, and it says, write a function g whose graph represents the indicated transformation of the graph f. And we're given f of x equals x plus 6. So what would g of x look like, or we can simply call it g, if it's taking f of x and we're translating 3 units to the right? If you translate 3 units to the right, what you need to do is you need to add or subtract 3, and you would come up with x plus 3. So you're subtracting 3 to whatever value is connected with the x by addition or subtraction. And the reason that you subtract is because if you think about it graphically, what you would need to do originally, if you input, say, if you input 0 into x, you would originally you would have an output for f of x. If you input 0, you'd have 6. But this new graph is translated 3 units to the right. So instead of having an output of 6, you would have to input 3 to get the same output. That can sometimes help with graph if you can understand it graphically. So let me show you graphically what's going on. X plus 6, by the way, what does that look like?
Isn't it a vertical line?
It is not a vertical line, no. It is not horizontal. It is a line. It's definitely linear. It's a degree of 1. And the lowest degree is a constant, so it's definitely linear. What is what's its slope? Maybe that'll help. Its slope is 1. Right? The coefficient of x is 1. It's not written, it's understood to be 1. And what is the y-intercept? Thank you. We plot this guy right there. And it has a slope of 1. So that is up 1 over 1, up 1 over 1. Up 1 over 1, up 1 over 1. We go ahead and graph it. Use preferably a straight edge if you have it. If you have one. So that would be the graph of f of x equals x plus 6. And they want this shifted 3 units to the right. So when we do transformations, you are allowed to apply the transformation to individual points. Or you can view the whole thing being moved over. But when they become more complicated, I think it's easier to do point by point. So we want to graph our new function. I think they use g of x, yeah. And so 3 units to the right. So this guy, I can go 1, 2, 3 and plot it there. This guy, instead of being an output of 2, 8, let's see here, it would be 3 to the right. So 1, 2, 3. Again, and if you use graph paper, it'll be even better than this, because this is, human error. Graph paper is even better. So go ahead and do that every time you can. And we'll go ahead and graph these things. And they should be parallel. Right? They should be parallel because they're going to have the same slope. We're just translating, which is just like shifting it exactly 3 units to the right. And so what I'm saying is, if you want to shift to the right, what you do is you end up subtracting 3, which at first seems counterintuitive. So we do x minus 3, and we still have this plus 6 here. I know this simplifies, but I want to leave it in this form now because it allows for better understanding the more complicated these functions get. And they're not just linear when they're quadratic or what have you. So according to what we know intuitively, if I input 0, I got 6. I know looking at this, if I input 0 into my new function, it looks like I would only get an output of 3. Does this make sense to approach it like this, to understand this? Does it make sense the way I graphed it?
I understand why you graphed it that way,
Okay.
but like this, why you put input 0, I don't understand that. Like, I remember the chart, but I still don't remember, like, I don't know.
If I input 0 for f of x, I get an output of 6. Now, according to, you said you understand the graphical part of it. According to my graph, if I input 0 and for x for g of x, which is red, I should get an output of 3. Let's see if that's true. If I plug in 0 for x.
What do you mean output? Like, that should be.
Okay, so let's go over this, outputs versus inputs. So that's a good question. So let's clarify some things about functions. So when I say output, that is the value of the function. That is your g of x or your f of x, depending on which function we're talking about. That's your output. Your input is the independent variable, x. So if I say I input 0, I'm talking about substituting 0 for x. What is the value of my function? Or what is my output?
I want to know how you got x minus 3.
Because this is a shift 3 units to the right. I think about, you can think of it like this. I have to input a value that is 3 greater to have the same output. You notice these two have the same output at this here. I had to input a value that was 3 greater. So if this had an input for 2 to get this value, I had to input a value of 5 to get the same value. That's why you can think of it as kind of like the opposite, why you end up subtracting. But going back to the simple part, this part here that I was discussing, if we input 0 into our function f, we get an output of 6. If I input 0, according to my graph, if I input 0 into g of x, I get an output of 3. Let's see if that's true from the way what I have written. 0 minus 3 is negative 3, and negative 3 plus 6 is 3. If I had made it what students first think it is, at first they think, okay, well, I would add 3. It wouldn't be correct because I would input 0 and I would get an output of 9, which is not correct. So this would satisfy that problem. Simplifies to x plus 3. So if we translate left and right, so translation 3 units to the right, we subtract whatever that translation is from our x. So what do you think number 2 would be? F of x equals x minus 3, and we want to write g of x where we take f of x and we translate it 1 unit to the left. We would add, yeah, which would leave you x minus 2. Because it's like you have to make up for it.
Yeah.
You think of it like that. You have to make up for it. And you might want to write that in your notes to think intuitively. You have to make up for it. And here's the great thing too. If you ever get lost in this process that I'm doing where I add or subtract values, you can always go back to, okay, I'm going to do it graphically what it says, and then you can see, okay, I can see what the input would, okay, this is what the output is. Okay, so it would have to be this, kind of like how I just demonstrated for number 1. Number 2 would be the same exact demonstration if I graph g of x. Now 3 is the one that's different because the translation is not left or right, it's up or down. This is the one that's very intuitive. It's exactly what you would expect. If I write g of x and it needs to be taking f of x but translated 1 unit down, well, think about whatever I input into x for f of x. I do this, minus 2, absolute value, and the last thing I do is minus 3. Well, the constant that's completely by himself, that is a vertical translation. It doesn't matter whether it's absolute value, quadratic, any sort of polynomial, cubic. when the guy is on the far outside, it could be even exponential or radical. When you have a constant completely out by itself, that shows you what's going on vertically. So if you want to take this guy and just go one unit down farther, you would subtract 1. So this is the one that I guess is the easy one. Where if we're going down, subtract 1 on the constant term that's outside by itself. If I'm going up, I add 1. So this would end up being g of x is equal to the absolute value of 5x minus 2 minus 4. So these two functions are both linear. This is an absolute value function. It looks very different. Does anyone recall what an absolute value function looks like, just in general? Yes?
You just have a straight line. Right there. And then you got absolute value.
Think what shape does it look like? What letter does it look like in the alphabet?
Oh, you're talking about that.
It is a V. It is a V. Yeah. These are the absolute value bars. So this is saying f of x is equal to the absolute value of 5x minus 2, and then whatever that is, minus 3. It's the one that's a V. It's the one that is going to be like this or like this. I'll go ahead and I'll add that. Some additional. So let me give what's called the parent function. And this is something that we started to touch on. This is absolute value. And this one specifically is the parent function. Parent function, you can just think of, it's the most basic one. There's no adding or subtracting of a value inside the absolute value bars with the x. There's no adding or subtracting some constant on the outside. It's just the basic guy. That's what they mean by parent function. Because then what we're going to look at is comparing these, taking the parent function and comparing some other function that's the same type, kind of like number 3 we just looked at, and seeing how does that compare to the parent function. So what this looks like, by the way, let me see if I can make this a little better. I'll actually do axes using straight lines. And let's do some marks. Can anyone tell me what absolute value means? You guys remember from Algebra 1 what absolute value means? Absolute value is the distance from 0 on the number line. That's it. So definition. Definition of, I'm just going to abbreviate in my room, absolute value. That's just the distance from 0 on the number line. Can you guys read my handwriting? Better than a doctor's, but not as nice as the handwriting on the whiteboard. Distance from 0 on the number line.
Reads your record.
Yep. Oh, great thing to point out now. Desmos.com. I know I've mentioned it to you guys before, but in case you missed it, I just want to emphasize that is the best online graphing calculator, and it's very mobile friendly. So when you guys are doing these problems, and it's like, man, I want to know what this looks like, or I want to check my work, Desmos.com can graph pretty much anything. You don't even need the app. If you go to Desmos.com on your smartphone, it's very clean, very nice. A lot of times when I'm sitting down and I'm doing something with a student, I'll have it on my laptop, Desmond.com, off to the side, and quickly punch in a function and see, understand it graphically. So what does this look like? So what I'm going to do is I'm going to use straight lines, because these are going to be straight lines. And let's see if we can do this. Oh, I missed it. Pretty good. That is what absolute value looks like. F of x equals absolute value of x. So let me briefly explain why it looks like this. So if you think of absolute value, again, these are just real numbers. If you think of absolute value as the distance from 0 on the number line, so if I say, okay, when x is 1, well, what is the distance that 1 is from 0 on the number line? It's 1 away. Well, what's the absolute value of -1? Also 1, because it's distance from 0. This is why there are no negative values for the function, because it's just distance. So there's no negative values for the basic parent function, f of x equals absolute value of x. Now, if I shifted it down, if I put a -3 on the outside, I would just do this exact same graph, just shifted down. So why don't I put that on there while we're here? Let's say if I had g of x is equal to the absolute value of x, say -3. One, two, three. And again, these lines would be parallel. There you can see g of x equals absolute value of x -3. The -3 is on the outside, so just vertical shift down 3 units. So we got these 3. Now we're going to look at where we need to be here, because we're studying. We just started to study quadratics now, so we're going to get some more information on what's going on. How do the constants a, h, and k affect the graphs of the quadratic function g of x equals a, parentheses, x minus h squared plus k? So with the value, now notice it's written as x minus h, because we noticed what happens to be the tendency. If we say, okay, a new graph is going to take the parent, this guy and shift it to the right, we ended up subtracting. That's why it's written as x minus h squared plus k. This is called, now it's not written on here, and I can't write on this particular slide, otherwise I would. This here, you need to write in your notes, this here is called the vertex form. This is called the vertex form of the quadratic. And the standard form, which you might want to write along next to this, is the ax squared plus bx plus c. Okay, so we know that the h is translation left to right. We know the k is moving up and down, so now we're going to touch on this a that's in front of the whole value x minus h squared. Now the parent function, meaning the basic form of a quadratic, the parent function is just f of x equals x squared. Go ahead and write that somewhere for this information here. I can't write on this slide, otherwise I would. So the parent function is just f of x equals x squared. Actually, it looks like I can. This one I did. The other ones I couldn't. Okay. So let's do that. The parent function is just, say, f of x equals x squared. So if h is positive, translation h units to the right. And then if h is negative, translation h units to the left. If k is positive, then that's a translation k units up. And if k is negative, translation k units down. And then now, last but not least, is the A. If the bell rings, this is going to be on Blackboard. If A is greater than 0, that's called a vertical stretch. By a factor of A. Absolute value of A is greater than 0. And then if the absolute value of course, is greater than 0. Sorry. Greater than 1.
Are you serious? Oh, is that what you over Zach's house?
And then if the absolute value of A is between 0 and 1.
Oh, okay. Yeah, I can do it with
We'll pick back up for your next class, so don't worry. You too, thank you.